Questions about anything? So the exam is next Wednesday in class. I'll bring paper and then the exam sheet. And all you need to bring are pencils and eraser because it's a closed book, no notes, no computers, etc. kind of exam. Anyway, there's more information on the homepage about that. But if there's any questions, let me know. So today I'm going to prove a famous theorem called the open mapping theorem, which is a special property that analytic functions have. If f is analytic on a domain or just any open set, well, let's make it connected. So it'll be a open connected set as a domain. Then if f is a not constant analytic function, it maps open sets to open sets. And so in particular, the image of omega would be an open set in the complex plane. And of course, we know topology says that a continuous mapping maps connected sets to connected sets. So now we know the image is open. It would be connected just by topology. And so it's a domain too. So I'll say more about that in a minute. But I'll call this the OMT. It's important to realize that this is way false for real valued differentiable functions. A very simple example, let's see, the easiest example I can think of is if you take h of t equals 1 minus t squared. And you'll notice that h of the open interval from minus 1 to 1 is equal to, let's see, that's equal to 0 to 1, but that's a parabola upside down, and it assumes a maximum. So there's something related to kind of a maximum principle and the open mapping theorem. That's a very natural thing to suspect. But because that has a maximum, that image of that open set is not open. It's semi-open. And you can come up with other examples that do botch up both endpoints. But of course that thing is connected, so. But it's not open. Questions? Let's see, I guess this is a good moment to review some notation. Let's see, we'll write, let's suppose we have f mapping the domain omega into C. We'll write f of u of a set. That's equal to the set of z in set of f of z, such that z is in U, the image of that set. And another standard notation is f inverse of U, means something slightly different. Since we have a domain here, the domain of the function, that'll mean the z in omega, such that f of z is in U. And let's see, when you learn this notation back in some place, then it's a fact that f is continuous another way, that everybody knows the epsilon delta definition, but an equivalent to the epsilon delta definition is that the inverse image of an open set is open whenever U is open. Okay? If you haven't seen that someplace, well, it's a very simple thing to prove. You take your open set to be d epsilon about something, and you realize you'll get a d delta, and those are the epsilon and deltas in the definition of continuity. Okay. Well, I'm going to use the argument principle to demonstrate the open mapping theorem. Okay, so here's the proof. Proof that the argument principle implies the open mapping theorem. There's various different paths to the open mapping theorem. Stein, you'll notice, proves the argument principle implies Rouché's theorem, and then he shows the Rouché's theorem implies the open mapping theorem. That's a nice way to do it. I'm going to do it a different way. So let's suppose we've got a non-constant analytic function. So f is not constant, and analytic on my domain omega. Actually, I just want to show that f of omega is open. We want to see f of omega is open. Because then I could always take disks. I could take my omega to be a disk. And if I can show that the image of a disk is open, then of course that'll give me that it takes open sets to open sets. So this is, if I understand this just for this case, I'll be done. Because then I'll have it for disks. Okay, so suppose W naught is a point in that image. F of omega. Well, let's see. So it's in f of omega. Then so that means there exists a z naught in omega. This is just by definition of that symbol, with f of z naught equal to W naught. Okay. I next. So note that f of z minus W naught is not constant. Because f is not constant. So the zero it has at z naught is isolated. So there exists a radius bigger than 0 such that I can stick a disk in there dr about z naught closure is omega is open, so there's a disk in there, and I can shrink it down so the closure is in there also. So there exists disk so that and that's the only 0, and z naught is the only 0. Of f of z minus W naught in that closed set. Okay, let's let n equal to order of that 0. So that n equals, or multiplicity, equal to order of the 0 of f of z minus W naught at z naught. We say that that's the, we say that f of, here's what we say. We say that f of z equals w naught with multiplicity n so it's like a double zero. Well, this is hitting, if it's equal to 2, then this is hitting w naught twice. That's the way we think about it. With the multiplicity n at z naught. At z equals z naught. Okay. Now I'm going to draw a picture. So I'm going to take this circle of radius r about z naught. I'll take it parametrized in a counterclockwise sense. So that's going to be cr about z naught. And of course, that's parametrized by z of t equals z naught plus r e to the it as t goes from 0 to 2 pi. And then I'll have a z naught in the center there, and this will be my open set I'm thinking about. Okay, and I'm going to take my f here. F is going to map that picture. It maps z naught to w naught, and f might wrap that curve around a couple times maybe. I'll make it go twice around. Okay, and here's w naught. I know from experience that analytic functions smear open sets around. So actually this is going to get smeared around, and it's got to look like this. And I know also that everything inside this inner loop gets hit twice, and everything in this part between these loops hits once, and nothing gets hit outside this picture. After I explain this stuff, you'll feel that way too. But that's the fact I'm going to be showing you today. And let's see, I'm going to call this curve f of c of r. That's a curve, and it's parametrized like that. It'll be parametrized by the z of t is going to be f of z of t, the image. And of course, the t is going to go from 0 to 2 pi. Okay. That w naught is an isolated 0, so notice that. Let's think of f of zt, f of z of t minus w naught. That's never 0. Is non-vanishing. And it's obviously a continuous function. So it's a non-vanishing continuous positive function. What's a non-vanishing continuous function on closed interval 0 to 2 pi? So it assumes its minimum. So it has a minimum, and a minimum is positive. Positive minimum. Let's call it m. Okay. So let's see, m there would probably look like this distance to the closest point when it goes by. So I want a little disk that's slightly smaller than that m. So let's pick a row with 0 less than rho less than that min. Then the picture would be, I'd have I can put a little disk here. It would be, this is going to be my row. It's like that. It's within that minimum, so it's completely contained in the picture like that. It doesn't intersect the curve. In fact, it stays away from the curve by a distance of m minus rho. Anyway, I claim that every point in that little disk is going to get hit. So if I pick a W right here, that W is going to get hit. So my claim right now, let's see, that little disk of radius rho about W naught is going to be contained in the image of my disk. I never called this something. This is radius R. That's going to be contained in my disk, image of the disk of radius R about Z naught. So that totally gets hit. And that's going to allow me to stick a little disk around W naught that gets hit. And so that means that W is an interior point. So that all the points are interior points means it's open. The image is open. Okay. And so the key here is the argument principle. Okay, I'm going to use the argument principle. The number of times F hits W inside the circle of radius about Z naught, that's equal to let's see, that's the number of times F hits, that's equal to the number of zeros of F of Z minus W counted with multiplicity. That's what I mean, how many times it gets hit. I actually just want to show it's bigger than or equal to 1. So it's the zeros of that counted with multiplicity. And that's equal to, by the argument principle I proved last time, that's equal to 1 over 2 pi I integral around my circle. The hypotheses are satisfied because this has no zeros on that thing. And so let's see, in the top is f prime of z. Let's see, what's my function? My function is actually f of z minus w. That's the f. And the derivative of that thing in the denominator, because w is being held constant, is f prime. So it looks a little different than usual because but it's because the derivative of the denominator is just f prime of z, dz. Okay. And notice that's a function of w. And it's an integer valued function of w. And if you've ever done anything in analysis, you realize, oh, sure, this is no sweat. That is a continuous function of w, right? And you just look at it and you know it is because nothing's blowing up, everything's in sight's continuous, you got a compact set. So in fact, a knee-jerk thing to do would be to show that's continuous just by really standard analysis. And that's what Stein likes to do. But I've always liked to realize not only is that continuous, that's an analytic function of W. So let's notice, first of all, notice that we know what the multiplicity of that thing is. Notice that h of z naught, W naught gets hit n times. That's because the multiplicity of that 0 is n. We just want to see that we just want to see that h of w is bigger than or equal to 1. but it's actually going to be equal to n. So it's actually going to get hit n times when W is in that disk of radius rho about W naught. Well, my claim right now is that actually H is analytic. H of W is analytic on that disk of radius rho about W, and so continuous. So, in fact, it's an integer value continuous function. So it's an H is analytic on it, and so an integer valued continuous function on a connected set. On connected set disk of radius r about z naught. And so it's constant. That's a very elementary thing to prove. Let's say if it was two different integers, then you take a curve connecting the 2 points that map to those two different integers and use the intermediate value theorem. It would have to go through all the intermediate values, which are not integers. There's lots of non-integer values. So if it's integer valued, it can't possibly go to a different integer without going through everything in between. That's all there is to that. And so constantly equal to n.
Should that connected set still be d rho w?
Let's see. I've got a. Oops. It's. I'm sorry. You're right. This is d rho w naught. Thanks. It's analytic on that set. There, that's starting to get fixed. Okay, so let's see. Well, that's not going to be hard. Let's write what h of w. I just wrote it down. Do I need to? Let me copy it. Okay. Okay, h of w equals that. And now let me, let's see, that's going to be, that's the integral from 0 to 2 pi of f prime of z of t over f of z of t minus w, and the dz is z prime of t dt. And then you say, look at that for a second and say, aha, this stuff right here is d by dt of f of z of t by the chain rule number whatever, one of the chain rules. And this thing is the parameterization. And so we see, aha, that's how we would parameterize the other curve. So that's that's 1 over 2 pi, the integral around f of c of r of z naught. And let's see, that top thing is just the d by dt of the parameterization. So that's 1 over zeta minus w d zeta. That's a famous thing. That's called the index of that curve. So that's this is a remark here. That's equal to the index of w. Let's see. This is where the curve goes. That's the index with respect to this curve of the point w. That's the winding number. That's the index or winding number. That's the number of times that curve goes around that point. Index or winding number of the curve in the counterclockwise direction. See, the curve is f of c of r w naught of a, doggone it, f of c of r z naught. Have I been doing that? No. In the counterclockwise direction, it's the winding number about W. Okay? That's the definition of that symbol. And let's see. We know that that's a differentiable function of W because that was homework 2, number 1. Homework 2, problem 1. That's analytic. So I'm done. I showed that every W in there gets hit. And so that shows that image is an open set. Questions about that? Let's see. I'm gonna, now that I've told you that's the feeling for that is it's a winding number, let me go back to that picture I drew. Think about if you're standing here at W. All right, think of a bug crawling around this circle. All right, that would be the F of the bug would be crawling around this circle. So as the bug goes around there, the bug would crawl around like this and then go around again. So if I were standing at W and pointing at the bug, I'd spin around twice. And I'd spin around in the counterclockwise direction in this picture. So the winding number inside this thing is 2. But if I stood in this zone here between those curves and pointed, well, the outer one would go around me once. But I just go back and forth when I point at the bug going around this one, the inner one. So that doesn't add to the number of times I spin around. So I only spin around once here. So in fact, all these W's would get hit exactly once. And out here, the fundamental Cauchy's theorem would show me that then nothing gets hit. So that's how we understand that. And that's how the argument principle, in combination with that topology, is how it's going to work. Anyway, I'm not talking about winding numbers today. I'm going to do that later, but I wanted you to see that symbol. So I guess I should mention that we're done. Done. So what I've shown you is that the disk of radius rho about W naught is contained in a f of omega. And W naught was arbitrary. So we see that f of omega is open. Questions about it? Well, that's one of the big classic theorems of complex analysis. I guess the simplest corollary is that if f, let's say we have, suppose f is analytic and not constant, on a domain omega. Let's make it a domain omega 1. Let's let omega 2 equals f of omega 1. Then then we have then omega 2 is a domain. A domain 2. And so you would get F would be a mapping omega to omega 2, and this would be an onto map. Of course, just by the way I defined it. And the proof is just the open mapping theorem. Because if I had a domain here, there's a domain, it could have a hole. Okay, I know that the image of this thing would be an open set. And so, okay, it might have a, might go, do something weird like that. Here's that hole. So obviously the topology could get weird. It could add more holes, but at least I know the image is open. So this thing is open, check. That's the open mapping theorem. Okay, so here's omega 1. Here's f of omega 1. So it's open. That's the open mapping theorem. I have to see it's connected. So let's see. I'll take a point here and here. I want to see there's a curve connecting those 2 points. Well, the obvious thing to do, let's see, those 2 points are over here someplace. So here's one and here's the other. And to get a curve connecting them on the image side, all I do is take a curve here connecting them. Let's call this Z1, Z2, and this is going to be a W1, W2. And then the image of that, the curve on the left, would be the curve I'm looking for. So I took 2 random W's and found you a curve connecting them in the image. That's how you prove the classic fact that continuous functions preserve path connectivity. Questions about that?
I have a quick question on the open mapping theorem.
Yeah.
Where do we use that the analytic set of F was a domain?
I didn't.
So that just works for...
That follows. I didn't have to use that because it's a simple corollary. I just had to show that it takes open sets to open sets. Then it's topology that means that.
Okay, so we did require domain.
I didn't require. I did well to be non-constant. If it didn't have a domain, you'd have one open connected set here and one here. Maybe it's not constant here, but it is constant over here. So domains, we know this fact that a non-constant function, for example, has isolated zeros, and that requires a domain. Otherwise, on one blob you could have isolated zeros, but on another blob it could be identically zero. So it would screw up that kind of thing. That's why we always study analytic functions on a domain, so we don't have that weirdness. Let's see another corollary of the open mapping theorem. Is a weird special property of analytic functions that if they're one-to-one, their derivative has to be non-vanishing. So let's suppose we have f omega 1 to omega 2 is one-to-one and analytic. Let's make this is... Let's suppose I have analytic on domain omega 1 and 1 to 1. Let's let omega 2 be f of omega 1. Then we know omega 2 is a domain. And we get f from omega 1 to omega 2 is going to be 1 to 1 and on to. And of course we know this omega 2 is a domain. By the way, it being 1 to 1, it's not constant. One to one implies not constant. Well, that if I have this map that's 1 to 1 and onto, so the inverse exists. Let's let f equal f inverse. And that's going to map omega 2 to omega 1. Well, this corollary says that let's note that the open mapping theorem implies that the inverse is continuous by that remark about the definition of continuity. F inverse of u equals f of u. I'm sorry. I want to see that f is continuous. So f inverse of u is equal to f of u, and that's open. So check. Well, the interesting thing is that f is actually analytic. So 1, f is analytic. On omega 2. And the derivative is non-vanishing. And 2, f prime of f of z is equal to 1 over f prime of z, and f prime of z is non-vanishing. So f prime of z is non-vanishing. On omega 1. So being 1 to 1 means it has non-vanishing derivative. That is way false for real functions. So that's a way false thing, R to R. The classic example is h of t equals t cubed. That's infinitely differentiable, and it's maps minus 1, 1, 1 to 1 onto minus 1, 1. So it's 1 to 1 onto. And of course, the inverse map is the cube root, and that has a nasty non-differentiable singularity at 0. H inverse of tau would be tau to the 1/3. Not differentiable. At t equals 0. Okay, so let me demonstrate this theorem. Oops, where am I here? Here's the proof of this little thing. Let's see, f is not constant. So f prime is not identically 0. Not constant, so f is not identically 0. So the zeros are isolated. Okay, so let's suppose I have one of those zeros. F prime of 0, z naught is equal to 0. Then I'm going to I'll do a picture like this. I'll have a z naught in the middle here. I'll shrink it down so it's the only 0. And then I'll have f. F is it's gonna map that to a blob. It's gonna be a 1-to-1. So this is gonna be my u. And f of z naught is gonna be equal to w naught. Okay, so let's see. F was 1-to-1. So when this u is equal to let's call this disk of radius epsilon about z naught. This open set is going to be f of the disk of radius epsilon about z naught. That's going to be open and connected, and this f being 1-to-1, this is going to be a 1-to-1 onto. Okay.
Should this be f prime?
No. I just know that, I just want that to be an isolated 0 of the derivative. Okay, so what do I know here? Everywhere else except that weird spot, the inverse is analytic. So the f going this way, capital F, we see that f is analytic everywhere except w naught. That's where the derivative is 0. Every place else, the thing is analytic. And so we see that f is analytic on u minus w naught and continuous up to w naught. So the Riemann removable singularity theorem implies that w naught is removable. Okay, and now, when you think about that, let's think about f of z, capital F of little f of z is z. Everything in sight there is analytic, and so I would have that f prime of f of z times f prime of z is equal to 1. And we see that those must be we see that neither one of those things can vanish because they're both analytic. So what we see right here, f prime of z can't vanish. So I assume that there was an isolated 0 at z naught, But it can't be an isolated zero because I can do the Riemann removable singularity to the theorem to the inverse. So that's why this is kind of a sneaky proof that involves something special about analytic functions, namely the open mapping theorem. Let's see. Got 5 more.
I have a quick question.
Yeah.
For the showing that W naught is removable, are we using the Riemann removable? Because we're not showing anything's bounded. Are we using...
Right. So I mean it's continuous, so it's bounded.
Oh.
But that I have called that the Morera. What did I call it? Gorza-Morera version of the removable singularity theorem. But you're right. So that was a theorem I named, but I could use the Riemann removable singularity theorem because being continuous there means it would be bounded in that near there. So that would be removable. Anyway, I feel like I'm running out of time and I don't want to get carried away here. Next time I'm going to do a review. But after the exam, the inverse function theorem, which is going to turn out to be very simple. Inverse function theorem for analytic functions. Anyway, this open mapping theorem makes it rather easy. So it's going to be easier than the real version you learned. Because we have this geometrical feeling for the argument principle and the open mapping theorem. So yeah, to prepare for Monday, the review, I would suggest you look at the old exam and the practice problems, and if you see something that, try something you can't figure out, that's a good thing to ask about. And I'll go over those things on Monday and answer all questions you might have about those problems or homework or whatever. Okay, that's enough for today.
This is how it's used. So this represents some. Yeah, how do we know what I can do? Because I assume if this diverges, that diverges. I don't really know, but I assume there's a theorem where basically this has the same rate. Basically, 90% of the error exactly. I'm not sure, but I'll try to prove it, and then I would need to take that works as a small warning. That's what I didn't know that. But yes, that power station.
They posted on the homepage, yeah. What's
What's
that? No, I want you to think about them before I give you the answers.
Question for the exam is the material coverage, is it like up to last Wednesday or is it Wednesday or today or?
I'll send an email. The open mapping theorem is just a pretty simple statement, but yeah, I probably won't have a question about it. So maybe I'll say Wednesday.
Okay.
I'll send an email just to be clear about
Sounds
that.
good. Thank you.